So today we want to continue talking about the graphs of polynomials. And so one of the things that we need to know as we are dealing with polynomials on the graph, if you recall, we have lovely pieces of that graph called x-intercepts and y-intercepts. Okay? These give us some insight into where exactly on the graph this polynomial happens to be. So if you recall, you have a y-intercept is where it crosses the y-axis. Now polynomials are functions. That means they pass a vertical line test. So you cannot have more than one y-intercept. And you are always going to have a y-intercept when it comes to polynomial functions. So there should be one and only one y-intercept. What you may notice in this particular graph is that it definitely has more than one x-intercept. So x-intercepts are where we get some really interesting things going on with polynomial functions. And so we're going to spend most of our time today talking about x-intercepts, but I did want to talk briefly about y-intercepts. Y-intercepts are important. The y-intercept is where it crosses the y-axis. There is only one. And when an equation is in standard form, you can automatically know what its y-intercept is. Now, if it's in a different form, if it's not in standard form, you may need to be careful. But in standard form, the y-intercept is always the constant. Because we know that for the y-intercept, it's where x is equal to 0. So when we plug 0 in for all the x's in the polynomial, all of those terms go away because we're multiplying by 0, and 0 gets rid of everything. So then the only thing you are left with is the constant, the one term that didn't have an x in it. So anytime you're looking at the standard form of a polynomial equation, its constant is always its y-intercept. So you can find the y-intercept quite easily. Look for the constant. So that is your y-intercept. Most of our time today is going to be spent focusing on the x-intercepts. So let's take some time to talk about x-intercepts. So to find x-intercepts, we need to realize what the x-intercept is. So x-intercept, we have 5 words that we use associated with polynomials that use the same numbers. We use different words in different contexts because we're talking about different things, but when it comes to the equation and when it comes to the function and when it comes to the graph, these are all the same numbers. That's x-intercept, zeros. You may remember if we're using our calculator, zeros is the word that we key in on there. Roots, factors, and solutions. These 5 words are actually all talking about the same numbers. We use x-intercepts and zeros generally when we're talking about graphs. We use roots and solutions when we're dealing with the equations. We use factors when we're trying to factor a polynomial. So there are words that we use in different contexts when we are talking about different things, but when it comes down to the actual math of it all, they all are talking about the same numbers, which means that if I want to find the x-intercepts of a graph, I can factor to do that. If I want to find the x-intercepts, it's the same thing as the zeros, so I can use my calculator to find the zeros. If I know the solutions, then I know the x-intercepts. They're all interchangeable, and we're going to see that a lot next unit as well. That's going to be a big deal. But for our intents and purposes today, with the x-intercepts, what we want to talk about is that the degree of a polynomial tells us how many roots does the polynomial have. All right? This actually comes from the fundamental theorem of algebra, which is a really fancy worded theorem. But what it boils down to is any polynomial of degree n has exactly n, taking multiplicity into account, solutions or roots. So one of the things that is interesting about that, we did this with quadratics. It was x squared. And we talked about that quadratics have to have two solutions. It's because it's x squared. It is a degree of 2, so it has to have two solutions or two roots. Now, what we also learned, though, was that sometimes those can be real roots, and sometimes they can be imaginary roots. And what we also learned with quadratic is that the imaginary roots don't show up on the graph. So when we look at an equation and we look at its degree, we know how many roots it should have and how many roots it has to have. But we don't necessarily know how many of them are real and how many of them are imaginary. So that's where we just have to, pay attention as we're graphing and do a little detective work. But I do want to point out the degree tells us how many roots does the polynomial have, how many solutions does it have. But it doesn't tell us how many of them are real and how many of them are imaginary. Off of the fundamental theorem of algebra, you can also get a couple of corollaries, things that we get from theorems. And we also get another little rule that tells us that imaginary and irrational roots, so the imaginary root theorem and the irrational root theorem, imaginary and irrational roots have to come in pairs. Okay, imaginary and irrational roots have to come in pairs. Now, let's think about that for a second. Where do imaginary and irrational roots come from? An imaginary number comes from taking the square root of a negative number. An irrational number comes from taking the square root of a number that doesn't have a perfect square root, a non-perfect square number, something like the square root of 5, or the square root of 2, or the square root of 3. All right? So imaginary and irrational roots come from taking the square root of a number. We knew this in quadratics. To get rid of a square, you had to take the square root. And when you did that, we always had to remember that the square root of 4 is not just 2, but plus or minus 2. Square roots have two outcomes. You get positive 2 or you get negative 2. And so every time I take a square root, it is always plus or minus, because I could have gotten 2 times 2 to get 4, or I could have done negative 2 times negative 2 to get 4. So square roots always have two outcomes, which means anytime I get an I answer, I could not have gotten 5i as an answer unless negative 5i was an answer as well. I can't get the square root of 2 as an answer unless negative square root of 2 is also an answer. So imaginary numbers and irrational numbers always have to come in pairs. Now, why would that be important to us? Well, when we start trying to figure out how many x-intercepts our polynomial could possibly have, we always want to keep in mind that if we're going to have any imaginary ones that aren't going to show up on the graph, then they're going to have to come in pairs. All right? So here's how we can look at degree and associate it with some zeros, and how do we get the x-intercepts and all of these kind of things. So let's take, for example, we have our calculator. We're going to go in here and we're going to type in. All right, so let's take a look at, let's do y equals 5x cubed minus 3x minus, let's do 6. All right, so this is our polynomial. Now, just looking at it, I already know its end behavior. It's positive, so that means the right is going up. It's odd, so that means that the left is going down. So my right arrow should be going up. My left arrow should be going down. It's odd, it's a 3, so at most it can have 2 turns. So it's either going to turn twice, or it might only not really turn all the way around at all. okay? It just keeps going up, all right? This is going to be my cube function. That's what we learned yesterday. But we also know that if it is to the third power, it has to have 3 roots. Now we would call this 3 complex roots, because if you remember, complex includes the real and imaginary numbers. But if I wanted to know how many possible real roots could I have, how many possible real roots, I could have 3 real roots. It could cross the x-axis 3 times. But I could also have 1 real root. Because if it's going to have an imaginary root, then it would have to have 2 of them. I can't get 2 real answers and 1 imaginary answer. That's not possible because imaginary answers have to come in pairs. So I'm either going to have 3 x-intercepts or 1 x-intercept. If I want to know how many imaginary roots I could have, I kind of have to think in the opposite direction. I know I have 3 roots. I can't have 3 imaginary roots. Imaginary roots have to come in pairs. So it always has to be even numbers. Well, 4 is too many. It doesn't have 4 roots. It only has 3 roots. So that means that the most number of imaginary solutions I could have is 2. I could also have no imaginary roots. So they were all real and I had no imaginary roots, or I could have 2 imaginary roots. But it's not possible for me to have 4. It's not possible for me to have 6. It's not possible for me to have 3 or 1, because imaginary numbers have to come in pairs. So just by the degree, we know how many real possible solutions we could have and how many imaginary possible solutions we could have. That's important. We want to know what we're looking for. I don't want to sit here and waste my time looking for 5 roots if there's only 3 of them. And I don't want to just find 1 root when it's a 3rd degree and know, oh, that means there's 2 more out there. I have to find those. And that's going to be really important when we start solving. So your degree is always going to tell you how many possible roots you could have. I do want to point out that sometimes our real roots have what we call multiplicity. And that is that we get the same number twice. Now, it still counts as the fact that we have 3 roots, but you can get the same number twice. If we think about that from a, quadratic perspective when we were solving, if I factored something and it factored to be x plus 3 and x plus 3, then when I solved it, I got x equals -3 and x equals -3. I did get 2 answers. They just happened to be the same number. When you have multiplicity, that does look a particular way on the graph. And you can tell just from the graph whether that number has multiplicity or not. If you're talking about multiplicity and having a real number that is a solution more than once, multiplicity, when it is on the graph, it does not cross through the x-axis. What happens on the graph is that we actually have one of our turning points on the axis. Okay? We have a turning point that actually touches on the axis. So if this graph came up and then it turned around and then it turned around right there on that point, it doesn't actually go under the axis. It comes down to and has its vertex, so to speak, of that little turn on the axis. So then it looks like I only have 2 x-intercepts. But if it was x to the 3rd, we know that we have to have 3 roots, and there's just 2 here, but we can't have 1 imaginary root. So we want to make sure we can account for everything. That means that one of these roots has a multiplicity. And the way that you can tell it has a multiplicity, again, this one actually goes through the axis. It is in the negative, and then it becomes in the positive. But this root here, this 0, it was positive, and it's positive on the other side. It has a turn here. So this root has multiplicity. It is an answer more than once. And that's going to, again, become very important when we start factoring and when we start solving. It can look that way from underneath the graph as well. For example, if we came down below and then came up to the graph and it just touched the graph in that one spot. Okay? This would be the point that has the multiplicity. So lots of things that we can get about the graphs and from the graphs and important information that we need to know about the graphs and how that degree, that highest exponent, tells us about the x-intercepts. Now you can also see why if we did have an x cubed and it just had one real root, that means it has two imaginary roots. That means that somewhere up here it turned around, but it didn't actually make it all the way back to the x, to the x-axis. And that's usually what it looks like if we only have the one real root, but we know that it's got some other roots out there, some other imaginary roots. So the graph is going to turn around, but not quite make it all the way back to the axis. So that's what that looks like. We also need to make sure that we can use our calculator to help us find those zeros. So if we have, let's pull that calculator back up. If you have forgotten, when you go into y equals, you can just type in your polynomial. I think we will do x to the third power minus 2x squared plus 5x minus 8. And if we graph that, that's what that looks like. We can then use, if you remember on your calculator, second trace and go to 0. Because again, we want to know x-intercepts, zeros, they're the same things. And if you remember using the 0 function on your calculator, it always asks you for a left bound and a right bound. Because it is going to be testing every number to see which one gives it 0. It wants you to narrow down how many numbers it has to test. So when I look at this x-intercept, it looks pretty close to 2. So a number to the left of 2 would be 0. So I could type 1 or 0. The number to the right of 2 could be 3 or 4. So I can just type 3. And notice the arrows pop up there. And this happens to be in between there. So it should be fine. Don't guess. Just hit 0 or enter, excuse me. And then it will tell us that 1.7521718 is where that x-intercept was. So it wasn't 2, but it was close. This also happens to look like I have one real one, which means that there must be two imaginary ones out there. It doesn't appear to make it back over to this one. You can always zoom out to try and see if it turns back around up here somewhere and you just don't see it. But you want to make sure that you find all of your x-intercepts that you can and account for all of your roots.